So when you learn about the hypervisor, then you may go through the situation that you cannot see the source code in the real project. So in this case, it's necessary to review the hypervisor with the key component. So I think that this video will provide the guideline for the core component of hypervisor, even though you cannot see the source code of hypervisor. What is the key component of hypervisor architecture? And the first component is guest OS. The multiple operating system in the hypervisor environment is called guest OS. Let's assume that we have the two guest OS. The first guest OS could be the Android, and the second, the guest OS could be the embedded Linux. In some cases, first guest OS could be real-time operating system, and the third guest OS could be the Android. The manufacturer can choose their own the type of guest OS by some of the configuration. And another important component of hypervisor architecture is hypervisor. And then inside hypervisor, then what you can see is there are some of the routine that is associated with the ARM architecture, and another component you're going to see is the real-time operating system. Since the main job of hypervisor is to manage the workload of the multiple operating system, then each nature of the hypervisor could be real-time operating system at the software level. So even though it is impossible for you to take a look at the source code of hypervisor, and we have the XEN hypervisor that is used, that is open for the public. In the next video, I'm going to show you the key software routine in the XEN Gen hypervisor. And another key component of hypervisor architecture is the ARM architecture. So ARM architecture provide the several key features of virtualization. The virtualization include the virtual CPU, the virtual interrupt, the virtual address, and virtual memory mapped IO. Those kind of features can be implemented using the feature of ARM architecture. So we'll dive into more about the virtualization feature of ARM architecture in the next video. So this slide will show you how the hypervisor architecture is organized. And I'm going to explain the details of each component in more detail. There is two guest OS, and the first guest OS is here. So please take a look at this. Then first guest OS consists of the two software stack. The real-time operating system kernel is running at exception level 1. And as for user application, and it is running at exception level 0. Another important thing we have to remember is that guest OS 1 is running in isolated execution environment, in the isolated spaces. And as for guest OS 2, the Linux kernel is running at exception level 1, and user application is running at exception level 0. Like guest OS 1, the guest OS 2 is running in the isolated the virtual address space, and to allow for the guest OS to be run in the isolated area, that is one of the most important some of the environment for hypervisor architecture. Then in some cases, the guest OS wanted to communicate with the hypervisor, but in this case, if the guest OS wanted to interact with hypervisor, and software can use this assembly instruction. The first assembly instruction is HVC assembly instruction. HVC assembly instruction is called hypervisor call in terms of ARM architecture. And then we have another assembly instruction that is acting like HVC assembly instruction. That is WFE assembly instruction and WFI assembly instruction. As you remember, when the SVC instruction is executed in the user application at exception level 0, and then trap is taking place, trap is generated. Just like SVC assembly instruction, when you run those assembly instruction, exception can be generated by the ARM core. And then this arrow indicates this operation. What I mean is that if you run this assembly instruction and the control is passed from the exception level 1 to exception level 2. And those kind of operation can be called guest exit from the perspective of hypervisor. Guest exit is one of the most important features of hypervisor. Without implementing this feature, the communication between guest OS and hypervisor can be performed. This assembly instruction can be executed in another guest OS. Please take a look at this. So inside guest OS 2, execution of those assembly instruction can be executed like this. Then running this assembly instruction, and in this case, program counter is branched into this address. Those kind of address is called exception vector address. Then ARM core are doing the two behaviors simultaneously. The first behavior is to switch from exception level 1 to exception level 2, and then simultaneously program counter is branched into this exception vector address. The rule to branch into the exception vector address can be determined by this rule. So add the offset, the JRX 400, to the exception vector base address in the VVAR EL2 register. The VVAR EL2 register has the base address for exception vector table. So I'm going to explain about the responsibility of the VVAR EL2 register in the next lecture. And then another important features of the hypervisor is the real-time operating system. So if you review the XEN hypervisor, you're going to see the particular thread or task that is scheduled just like the task is scheduled in the Linux kernel. And then you're going to see another operation in the hypervisor at the software level. That what I mean is, if the interrupt is triggered, then hypervisor may take that interrupt, and those kind of the action can be performed with the level of real-time operating system. Real-time operating system is doing the similar task just like Linux kernel does. But the main job of real-time operating system in the hypervisor is to manage the resource of guest OS, or sometimes hypervisor, the real-time operating system in the hypervisor, is to allocate the particular virtual CPU into the guest OS. And sometimes the real-time operating system in the hypervisor may take the interrupt. Those interrupts can be designed to be taken to the guest OS. Instead, the real-time operating system in the hypervisor may control the specific interrupt. Then that real-time operating system in the hypervisor will some of the pass the control to the specific guest OS after it managed the particular interrupt. And those kind of features is implemented using the real-time operating system. So this is the key component inside Hypervisor. The another thing you have to remember is that ARM architecture. So ARM architecture is one of the most important features of Hypervisor, just like I mentioned in this slide. The HVC assembly instruction and WFI, WFE assembly instruction are introduced by ARM architecture. And then another features supported by ARM architecture is virtual interrupt. Virtual interrupt is only signaled with the support of the GIC, that stands for Generic Interrupt Controller. Generic Interrupt Controller is the interrupt controller designed by Corporation. So with this feature, the virtual interrupt can be signaled from the peripheral. The virtual CPU and virtual interrupt is one of the important features of Hypervisor that is supported by ARM architecture. So in summary, there are three important features, components that consist of Hypervisor. The first one is guest OS. Second one is real-time operating system in Hypervisor. And third one is ARM architecture. The next lecture, I'm going to show you another important control flow of Hypervisor. See you next time.